Welcome, everyone. Thanks for coming to our talk on Blink. I'm Xiaowei. I currently work for Alibaba. Before that, I worked for Facebook and Microsoft and a startup.
I'm Ma Guowei. I'm work in Alibaba. Previous, I work in Baidu. Thank you.
First, I'm going to give you some background on what Alibaba does. Alibaba is the world's largest e-commerce company. In 2015, we achieved the annual global merchandise value of almost $400 billion. This is much larger than eBay and Amazon combined. I currently work in the Alibaba Search infrastructure team. Our team is responsible for providing the personalized search and recommendation platform to most of Alibaba's search service, including Taobao, AliExpress, Alibaba.com, and Tmall.com. In today's talk, I'm going to first give some background on why we are using Flink, why we are investing in Flink, and what is Blink, the improvements we did in Blink, and finally, I'm going to talk about some challenges and future works we are working on. First, let me introduce a classical use case in search. In a search system, for a search system to solve the queries from user, first we need to build the documents that user want to be searched. In the case of Alibaba, a document can be an item, a listing that user can buy. Unfortunately, the data for a product is scattered in a lot of different places. Some data like item's price and item's description may be stored in a database like MySQL. Other attributes for products may be stored in some file system or in some other places. The job of search infrastructure is to assemble this information together to build a whole document which contains all the relevant information about a product. So this usually contains 3 stages. In the first stage, we synchronize the data from external data source like MySQL or distributed file system into a HBase cluster. Once the data is all in HBase tables, we do a second step that joins the data from different tables together, do some business logic, and merge them together to generate the final documents that can be searched. These documents are stored in the result table. It's also a HBase table. Once the result is in this HBase result table, it can be exported as a file or as updates to the search engine. Then the search engine can serve queries to the user. There are a few interesting things about this example. The first thing is I would like to point out is for each of these three stages, the sync stage, the join stage, and the export stage, they actually have 2 pipelines. The first pipeline is a full build pipeline, and the second pipeline is incremental build pipeline. So in the full build pipeline, basically we reprocess the whole data, all the documents. This is traditionally a batch job. The second pipeline is the incremental pipeline, which once the batch job finishes, the sellers may modify the item's description or even its price. And when a user purchases an item, the inventory may change. Such changes need to be reflected in the search result as soon as possible. To do that, we use the second incremental pipeline, which is traditionally a streaming job. So in this classical example, we really want to unify the approach for both batch and streaming. So let's take a look at how this was abstracted in a database community. This is a closer look at the second stage, the join stage. On the left side, we have an item table, and on the right side, we have a seller table. So in the full build stage, we will first try to join these 2 tables together, then use a user-defined function to apply some business logic and generate the documents that can be searched. This is pretty straightforward to describe in SQL. This would be the SQL that describes this logic. But how about the case in the streaming? For people with database background, he will immediately recognize this is actually a materialized view. So in a database engine, you simply need to create materialized view as this join. A materialized view behaves like an index. Index is derived data. Usually, you create an index, a secondary index on a single table. But the materialized view can be considered as a generalization of this. It can be created on a lot of queries, on a big subset of queries. Using this viewpoint, we can rephrase the classical search data processing as a materialized view. So a full build would be index creation or index rebuild. An incremental build would be equivalent to index maintenance. What does index maintenance is basically try to keep the result. So whenever a user modify the input table, the result table will need to be changed accordingly. The index maintenance process is responsible to maintain this consistency. So in this case, this means there will be some streaming kind of job that monitors the changes to the item table and the seller table, and accordingly, and updates the result table accordingly. So using this notion of materialized view, the database community unified the logic of batching and streaming. So let's try to use this logic and see how we can apply it to big data. I would like to introduce two concepts. The first concept is string and table duality. On the left side, you can see a string. In this case, the string will have two columns. The first one is a word, the second one is a count. So every time when the word counts, it has it records how many times this word has appeared in this so far. The second one is a table. If we use the string to update the table, you can imagine this table has a primary key on the current word. So if you use this string to update this history table, you will get 3 records because the second table, for example, the hello2 record will replace the previous one because there is a primary key on the current word. So using the process of materialization, from the string, we can get a history table. On the other hand, if you have a history table, and if you look at its changelog, you will get a string. So in some sense, the information contained in this string and in this history table are equivalent. They contain the same amount of information. There is one thing I would like to emphasize. Usually in big data, when we talk about table, people view it as something immutable. It never changes. But for this string and table duality, it's really important that table is dynamic. It changes over time. If it's immutable, the changelog wouldn't make sense. Yeah, usually, a table is associated with batch processing, and the string is apparently associated with string processing. Using this duality, we established a bridge between string processing and batch processing. When you try to express your logic in streaming, you don't have to think in terms of streaming. You just need to think about, if I materialize this string as a history table, how do I express this logic on this table? You are writing a batch query. Once you express this, your logic in batch mode, the streaming mode should give you exactly the same result. This is a pretty powerful paradigm, and that's something we would like to use to unify the processing of streaming and batching. Once we have defined this notion of string and table duality, we can define the second concept, which is string equivalence. Two strings are considered equivalent if at different times they produce exactly the same history table. To define this concept precisely, there are some subtleties to define this concept precisely, but I'm not going to be too academic. The most important thing is you get intuition. If you have two strings, maybe, for example, if the first string is missing the first record, they are still equivalent because once you materialize it into the history table, they will get the same history table at a lot of different times. This string equivalence gives us a lot of flexibility in how we can handle the stream. So in stream processing, there are different approaches. In some approach, they assume every operator in the processing is deterministic, which simplifies the problem, but it also limits the choice we can do. But Flink is very unique in the sense that it can deal with the undeterministic operator and still provide the consistency guarantee. This string equivalence is basically the theoretical framework that defines the consistency in Flink. The one important part of this string equivalence is if you use two strings to update the same MySQL table or HBase table, and they get the same table, these two strings are equivalent, which means sometimes you can correct your result. Traditionally, people in stream processing always require window to do any calculation. Because the string is never ending, you have to define some boundary to know all your data have arrived to get the result. But if you can change your result later, you don't have to wait. So window is not strictly tied to stream processing. With this approach, we defined the semantics of stream processing. This solves our first problem, the first challenge we have. We want agility. Our business needs change all the time, and we want a single code base that deal with both batch, the full build, and the incremental build. In addition, Flink also gave us a very high-level API that allows us to describe our business logic very simply. In addition to this agility requirement, the second thing we care about is consistency, which in this case it means if the database changed, this change has to be reflected in the final search result. We cannot lose the change. In this case, it's at least once semantics. And in some other use case, we have requirements for exactly once, and Flink can provide both. The next requirement is in the case when the inventory, when user buys the product and the inventory changes, this had better to be reflected in the search result very quickly, because if a product is to be sold out, it doesn't make much sense to rank the product very high, because if you do that, when user click the product, they will find out it's already sold out and cannot buy it. That's not the best user experience. So latency is also critical. And finally, in Alibaba, we deal with large amounts of data, which requires lots of computation. Anything that can process the same amount of data or do the same amount of computation more efficiently will help us greatly in saving the resource. So next, I'm going to talk about another use case we have. In search or recommendation, the algorithm engineers try different algorithms, and they want to evaluate how well each algorithm is doing. Usually, this is done like in a daily fashion, but we would like to do better. We would like to get the comparison at real time. This is what we do for real-time A/B test. The online logs, such as impression, click, and the transaction logs, are getting collected and processed by a parser and a filter, and later joined together, apply some business logic. Eventually, such data are aggregated, and the aggregated result is pushed into a current store like GUID. Once the data is in GUID, you can use a query to do a complex OLAP analysis on such data, and you can see how well each algorithm is performing. Last, I'm going to give the online learning use case. So this actually has two parts. The first part is real-time feature update. Some feature that we use in search ranking is things like the CTR, the inventory, and how many clicks you have. Such data changes over the time, And if we can if we can get the more up-to-date information, it will help us getting better ranking. So we have one pipeline to provide online feature update. This pipeline gave us a lot of benefit in conversion rate. This is usually enough, but in Alibaba, we have some sales event like Singles Day, which happens on November 11th every year. On this day, a lot of products are on sale with 50% off. So you can imagine the transaction volume is huge. It can be many times the transaction volume of a typical day. With this, the user's behavior pattern actually changes a lot. Whatever model you changed previously does not work well on this day. So to get the best out of it, we had better to have online machine learning. This is what we do. We use the log and use Flink streaming job to do online machine learning, which gave us a much better result in conversion as well. So this is, since you are here, probably I don't need to talk much about this. Flink is a unified computer engine. It unifies the batch processing and the streaming processing together. But one thing I would like to point out is there are two ways to unify it. The first way is use batch as the starting point and try to build a streaming solution on top of batch. This will not work well because the latency problem. Once you have once you try to do macro batching on top, to simulate streaming, you will have some fixed overhead. If you try to reduce the latency, the percentage of this fixed overhead becomes more and more, and it will be costly at some point. So it cannot be efficiently done. But Flink did it the other way around. It uses string as the fundamental starting point and try to build a batch solution on top of streaming. This actually works pretty well. A batch is basically a spatial case of a stream. It's a finite stream. With this approach, we do not lose the benefit of this of optimizations in batch mode, because in the case of finite stream, you can still do whatever optimization you would like to do in batch processing. That's the reason we decided to adopt Flink for all the scenarios I talked about. What is Flink? So we got excited and tried to use Flink. Then we discovered a few issues that could be a problem in our production use. So we decided to start a Flink project. It's a project that tries to improve Flink so it's suitable for large-scale commercial use. We have improved the Flink's table API comprehensively to make sure it's feature complete to all the use case we have. And in addition, we greatly improved the runtime. The important thing is the API is still 100% compatible with Flink. So all the high-level ecosystem built on top of Flink still works on top of Flink. Currently, the Flink is on production, running on a few clusters. Each cluster have about over 1,000 machines. And it supports mission-critical jobs like search recommendation. And we are doing some experiments with advertisement. We are also working with the data artists and the Flink community to contribute some of our works back to Flink. So I'm going to briefly go over some of the changes we did in table API. First, we introduced the concept of, I think fundamentally the starting point, the principle is we want the same SQL for batch and streaming, as we explained, just in the case of materialized view. From this starting point, we added a bunch of features to make the table API complete. In the current state of table API is pretty primitive, but we added these features. The first one is the user-defined function, which allows you to write business logic in functions, and the user-defined table function, user-defined aggregation. we also supported string-to-string join. This is one thing I want to point out. String-to-string join is highly non-trivial. But because Flink is a stateful computer engine, it becomes quite straightforward to do with Flink. That's the power of its runtime. And we add a bunch of built-in aggregations. The more interesting one is probably distinct count. We also added window support, including time window and count window. The last one is we added support for retraction, which unfortunately I don't have time to go into the details. Now, next I'm going to give my colleague Guowei to talk about the runtime improvements we did in Flink.
Okay, thanks, Xiaowei. Next, I will introduce the runtime improvements in Flink. First, I will talk about a new runtime architecture in Flink. Then I will talk about operator rescale. Then I will talk about incremental checkpoint. Finally, I will talk about async I/O feature. In Flink, there are two classed modes. The first is one is a standalone mode. The other is Flink on YA. In YA mode, Flink simply launch a standalone cluster with a fixed number of resources on YA. That means the job cannot request and release the resources dynamically. In addition, different jobs may run in same JVM process. That means the isolation is not very good. To solve the problem, Flink introduced a new runtime architecture. In Flink, every job have its own job master. The job master can request and release the resource as the job needs. Different job cannot run in same Java process. This resolves the problem of the isolation. Now we are working with the Flink community to contribute this back. In our production, our clients may need to change the parallelism of operators, and at the same time, they don't want to lose the state. But in Flink, it was impossible. In order to resolve the problem, we introduce concept of buckets. We have many more buckets than tasks, and each task will be assigned multiple buckets. When parallelism changes, we will reassign the buckets to tasks. Using this method, we make it possible to change the parallelism of the operators. In Flink, doing the checkpoint mainly have two stages. The first one is take a snapshot of the states locally. The other one is persist the snapshot of the states to HDFS. In Flink, the whole snapshot of states will be uploaded to HDFS. In production, if the state is very large, it is not acceptable. In Flink, we only upload the modified state to HDFS. Using this method, we improved the efficiency of checkpoint greatly, and we made it possible to use large state in production in production. In production, we find that bottleneck of many jobs are in accessing external storage, such as HBase. To solve the problem, we introduce the async I/O feature. The async I/O feature has two modes. The first one is ordered mode, which means the order of input elements will be preserved. The other one is unordered mode, which means the order of input elements will not be preserved. To achieve this result, we break down the normal process into 3 stages. The first stage, we will collect the listenable future. In the second stage, I/O threads will fulfill these futures. In the third stage, outputs of the completed future will be emitted. We also store the incomplete input elements into states for failover reasons. Using the async I/O method, our client can increase their throughputs greatly. Thank you.
Thanks, Guo. Now I'm going to talk about some of the challenges and the works we are working on. The first one is definitely continued optimization in streaming. This, especially in a few categories. The first one is how do we deal with back pressure in a better fashion? And the second one is how do we do faster recovery? These two are especially interesting and important in production. The second one is, as Stephen pointed out earlier this morning, we believe Flink has great potential in batch processing as well. We are working on this part to make sure we can fully leverage all the potentials in Flink's batch processing. We hope to get the batch mode in production in a couple of months. Next one is our business keeps growing, and we will need more and more machines, and our jobs gets larger and larger. It becomes increasingly important to make sure we can scale to even larger clusters. And I forget in these slides, we are also working a lot on the SQL support for Flink, both on the SQL part and table API part. Finally, but very importantly, we will continue to work with the community to contribute whatever change we made to Flink back to the community. I think we have a few minutes for Q&A.
Yeah, about the incremental checkpointing. How often do you do a full checkpointing? Because you cannot always do incremental checkpointing, right?
Yeah, so the way we did it is a bit different from Stephen was talking about. We always do incremental checkpointing, but RocksDB will do the compaction from time to time. When RocksDB do this compaction, we will also upload the compacted file. So basically, RocksDB is doing the compaction for us.
Oh yeah, I see. Okay, thanks.
Ben, thanks a lot.
Thank you.